Hi, today we're looking at gravitational potential energy. So we'll do a bit of refresher from last year. So in Physics 11, we just had for one gravitational potential energy formula, which was mass times gravity times r height above a surface or a height above a relative point. Now this formula only worked close to the surface of a planet with a known acceleration due to gravity. Now we also dealt with forces of gravity last year. So we had two forces of gravity formulas last year. We had, for one, where we had mass times gravity. That once again was only if we were close to a surface where we knew our acceleration due to gravity. If we weren't close to a surface or did not know our acceleration due to gravity, we had our universal gravitation formula of force of gravity is equal to g m1 m2 over r squared. Now, theoretically, each of those forces should equal each other. So therefore, if we wanted to solve for the acceleration due to gravity at any location, we can just cancel out our mass ones, and we get this formula for our acceleration due to gravity. Now, if we were to then take this g equals gm1, g equals gm2 over r squared and substitute it into the original gravitational potential energy formula, we end up getting gm1 m2 over r. So the reason why our r squared disappeared is because that r is canceling out with the y. Okay, so a bit more about gravitational potential energy. So with this formula, our potential energy goes to 0 as our radius goes to infinity, because we would be dividing by essentially infinity squared, which would mean losing potential energy as an object gains elevation. So that does not necessarily make sense to lose energy as we're gaining elevation. So due to that, we add a negative sign in front of our equation, which gives us a positive change in potential energy when we have an increase in altitude. So the formula on our formula sheet is EP equals negative g m1 m2 over r. If you remember, a capital G is a universal gravitational constant of 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Okay, so we'll look at an example. We have a 15,500 kilogram satellite in orbit 4.07 times 10 to the 7 meters above Earth's surface. We want to know the gravitational potential energy of this satellite. So writing off the information we have, we've got mass of satellite. We also have mass of the Earth, which we know is 5.98 times 10 to the 24 kilograms. What we don't actually technically know is what our r value is, because we're just given distance above the Earth's surface, so that's not center to center, which is what our r value is. And we need to solve for our potential energy. So if I draw out what we have a circle, which is our Earth, and the block that is the satellite. And our r, like I mentioned, is center to center. Now we're given the distance above the surface Earth, which is 4.07 times 10 to 7 meters. And then we know the radius of Earth is 6.38 times 10 to 6 meters. That's on your formula sheet. Now obviously this diagram is not drawn to scale, but it illustrates how we can get our r overall, which is just add those two values together. So that's giving us an r value of 4.688 times 10 to the 7 meters. At this point, we have enough information to find the gravitational potential energy. So we'll write out our formula, substitute our values in, and then follow bed mass, and we find that our gravitational potential energy at that height is negative 1.32 times 10 to the 11 joules. Okay, next example, if we have a 1.5 times 10 to the 3 kilogram satellite orbiting the Earth with a potential energy of negative 3 times 10 to the 10 joules, how far above the surface of Earth is it? So we know the mass of the satellites, 1,500 kilograms. The mass of Earth is 5.98 times 10 to 24 kilograms. Our gravitational potential energy is negative 3 times 10 to the 10 joules, and we're solving for R. So we'll start out with our formula of EP equals negative G M1 M2 over R, and we want to rearrange this to get R on its own. So first thing I would do is get R out of our denominator, and then divide both sides by our potential energy. At this point, R is on its own, so we can substitute our values in. Now when we solve this, we find that our R is 1.994 times 10 to the 7 meters. We, however, are not done yet because we're asking how far above the surface is it, not how far from the center of Earth. So if I draw out a similar diagram to that last example, we know that our R, which is center to center, is 1.994 times 10 to the 7 meters, and we know that radius Earth is 6.38 times 10 to the 6. So to get that distance from the surface to the satellite, we should be able to do some subtraction. So the height above is 1.994 times 10 to the 7 minus 6.38 times 10 to the 6 meters, which gives us a height above the surface of 1.36 times 10 to the 7 meters. Okay, so we're going to start looking at change in potential energy, because anytime we have a change in altitude, we're going to have a change in potential energy. So we can write out our change in potential energy as our final potential energy minus our initial potential energy. And if we substitute in our formulas for that, we get negative G times M1 M2 over our final R value minus negative G M1 M2 over our initial R value. Now you'll notice that for both parts of this, the only difference is our R value. So we can factor out the negative G M1 M2. When we do that, that gives us negative G M1 M2 times 1 over R minus 1 over R naught. Now if we want to get rid of the negative in front, we could just multiply it into those fractions, and we can also get G M1 M2 times 1 over R naught minus 1 over R. Okay, so we'll look at an example. We have a 25,500 kilogram satellite is being moved from the surface of Earth into orbit 4.5 times 10 to the 6 meters above the Earth's surface. What is our change in potential energy? So we'll start by writing out what information we have. We know the mass of the satellite is 25,500 kilograms. We know the mass of Earth is 5.98 times 10 to 24 kilograms. We know the radius of Earth, which is our initial height, is 6.38 times 10 to the 6 meters. And we know our final R would be that surface height, or the radius, plus how high above the surface, which would be 1.088 times 10 to the 7 meters. Now we have change in our potential energy as our final potential energy minus our initial. Substituting our values in and simplifying, just like we did on the previous page, and then substitute our values in, and we get a change in potential energy of 6.59 times 10 to the 11 joules. Okay, next example. when the Mir space station was disabled, what was its change in potential energy as it came back to the Earth? It had a mass of 450,000 kilograms and orbited at 402,000 meters above the Earth's surface. So, as usual, start out by writing out the information we have. We have the mass of the satellite, mass of Earth. We know the radius that it's going to end at, which is the surface of Earth. We also have our initial radius, which would be a surface of Earth, or radius Earth, plus how high above Earth's surface. So we get 6.782 times 10 to the 6 meters. And we're looking for a change in potential energy. So once again, utilize the same formulas, expanding it the same way, and substitute our values in, which gives us a change in potential energy of negative 1.7 times 10 to the 12 joules. It's negative, it makes sense because it is dropping to a surface, so it's losing height, so it should be losing gravitational potential energy.